Hello everyone, this is the another video in digital VLSI interview playlist. In this video, we will understand about the universal logic gates. As we know, this is the interviewer favorite topic, so we will understand this topic step by step. Let's start. So the first question is, what are the universal logic gates? Before that, first we understand what the universal logic gate means. A universal logic gate is a gate using which any Boolean function or any other logic gate can be implemented. Means using universal logic gate, you can easily implement any Boolean algebraic function or any other logic gates. So now if we will see what are the universal logic gates. So in digital VLSI design, there are two universal logic gates. First is NAND universal logic gate, and second one is NOR universal logic gate. Now let's see the second question. It is also an important question. So the question is why and NOT gate are called as universal gate. Now let's see the solution. So as we know that any digital circuit can be implemented or built using these three logic gates, AND gate, OR gate and NOT gate. So if there is a single logic gate that can implement these three basic gates, then we can say that it can also implement any digital circuit, correct? Meaning, let's say this is one digital circuit. This is one digital circuit. So if we are saying this digital circuit can be implemented using OR gate, AND gate, and NOT gate. These are three basic gate we have. So we are saying if this logic circuit and digital circuit can implement using these three gate, then if we are having one, let's suppose X gate that can implement these all three basic gate, then indirectly we can say this can also implement any digital circuit, correct? So what is the X gate here is? That is NAND gate and NOR gate. So that's why we are calling these two gates are universal gate, because with the help of these two gates we can implement these three basic logic gates: AND gate, OR gate, and NOT gate. Okay. So if we are able to implement these three basic gates with the help of these two universal gate, then we can implement any digital circuit using single universal gate. So that's why we are calling NAND gate and NOR gate as a universal gate. And why we are not calling AND gate as a universal gate? Have you thought that? Why we are not calling AND gate as a universal gate? Because with the help of AND gate, you can't able to implement all the basic gates. So what are the basic gates apart from the AND gate? OR gate and NOT gate. So we can't implement OR gate using AND gate, and we can't implement NOT gate using AND gate. So that's why we are not calling AND gate is universal gate, because for the uh, implementation, any digital circuit implementation, we need at least three basic gate. So if we are having any gate that can implement these three basic gate, then we can say that gate can also implement any digital circuit, correct? So like that we are calling NAND gate and NOR gate as a universal logic gate. In upcoming example, we will implement the whole function, Boolean algebraic function, or any basic logic gate using only NAND gate and using only NOR gate. So from there also we will get the more clarity on these both NAND and NOR universal gates. So from this question we have understood why we are calling NAND and NOR as a universal gate. So before starting the implementation using NAND gate and NOR gate, first we understood about the output behavior of NAND gate and NOR gate, and we will see the truth table as well as its symbolic representation one by one. So let's start. Let's see the NAND logic gate. NAND logic gate is a complement and the reverse of AND logic gate that we will see in the functional definition and as well as in the truth table also. So first we will observe the output behavior of non-NAND logic gate. So the output of NAND logic gate will be 1 when at least one input of NAND gate will be logic 0. So from here we can say whenever any input of NAND logic gate will be 0, then immediately the output of NAND logic gate will be logic 1. Okay, let's see the symbolic representation of NAND logic gate. So I'm drawing a journal to input NAND gate symbolic representation. So first input I'm assuming A and second input V, and the output is Y. Now we will write the output expression for the NAND logic gate. So it is inverse of AND logic gate. So we know the AND logic gate expression y is equal to A into V. So what will be the inverse of A into V? A into V var. Simple. Okay. And if you are able to see the difference of symbolic representation in between the and NAND, so the main difference is only this bubble sign. This bubble sign, it is nothing but it is a representation of NOT gate, because we are simply inverting the functionality of AND logic gate to make it as a NAND gate. Now let's draw the truth table of NAND gate. So as we know, we have two inputs. So the total possible number of input will be 4, A into V. So the first input where will be 0 0 0 1 1 0 and 1 1. Okay, we will write the respective output for the input pairs. We know from the definition of NAND gate, whenever any input of NAND logic gate is 0, then immediately the output of NAND logic gate is 1. So if we will to observe the first input pair, here both input are 0 0, so definitely output will be 1. Here also in second input pair, one input is set to the 0, then the output will be 1. And third input pair also the B value has 0 logic. So for this also the output will be 1. And if you will observe the last input pair, here A is set to the logic 1 and V is set to the logic 1. So here is no 0, then the output will become logic 0 based on the NAND gate definition. I am writing AND gate expression and output value in parallel of NAND gate for the comparison. So let's suppose I am taking the output expression as X of AND gate. Then we know whenever any input of AND gate is 0, then immediately the output of that AND gate is 1. So here both input is 0, then definitely output will be 0. And A input is 0, so the output will be 0. Here V is 0, then output will be 0. And we know whenever all input of AND gate is 1, then only the output is the AND gate is 1. Now if you observe, this expression is a reverse of this expression. So X is equal to by var. So from here we can conclude one thing. NAND gate is a inverse of AND gate only. Okay. Now let's see some basic questions of NAND gate. In first question there are two inputs and we need to write the output value for that NAND gate. First input is 0 and second input is A. And we know whenever any input of NAND gate is 0, then immediately the output of that NAND gate is 1. So simply we will write here y is equal to 1 because one input is 0. Now let's move towards the second question. Here one input is A and second input is 1. Now we need to write again the output of this NAND gate. Now if you will observe in the truth table, here whenever one input is set to the logic 1 in NAND gate, then the output of that NAND gate is inverse of the second input. Here if you can see the A value, A is 0, here A is 1, then what is the output value? 1. When A is 0, output is 1. When A is 1, the output is 0. And the condition is the second input is 1. So from here we can conclude one thing. Whenever one input of AND gate is tied to or set to the logic 1, then the output is the inverse of second input. So what we will write here? The output of this NAND gate is A bar because A is the second input. Okay, now let's discuss the third example in which there are three inputs and in which one input is set to the logic 0. So simply we can write the output value for this is 1 because whenever any input of NAND gate is 0, then immediately the output is 1. Okay. So hope so this NAND logic gate is clear to you. Let's see the NOR gate. It is also known as the complement of OR gate that we will see in the functionality and the truth table as well as. First, we will observe the output behavior of NOR gate. So the output of NOR gate will be 1 when all input of NOR gate will be 0. So from here we can say one thing about the NOR gate. When all input are 0, then only the output of NOR gate will 1. Now let's draw the symbolic representation of NOR gate. As it is a OR gate followed by the NOT gate. So according to that, we will draw the symbolic representation. It has two input in general and OR gate and follow it with the NOR gate or NOT gate. Sorry. So I'm simply writing this where A is a first input, V is a second input. Now what will be the output here? Here will be the output A plus V. As we know, this is the OR gate. And now after this, the NOT gate is connected. So the final output of NOR gate will be A plus B ka whole bar. Okay. And also we can write this whole symbolic representation in this way also. Here we will place instead of the NOT gate a vowel sign that will represent the NOT like this. So we can write in both way, but in general, this symbolic represent is used. Now we will see the truth table of NOR gate. As we know, it is having two inputs, so the total four number of combination input combination will be there. So what will be that combination? 00, 01, 10, and 11. Okay. Now we will see the output correspondingly the input. As we know, when all input are 0, then only NOR gate input will be 1. So in first case, if you will observe, all means both input are 0, 0. In that case, the output of this NOR gate for the NOR gate will be 1 according to the functional definition. And for the rest of the case, the output will be 0 only, because when all input are 0, then only the output of NOR gate will be 1. So for the rest case, the output will be 0 only. Now we will prove with the help of truth table why we are saying it is the complement of OR gate. So let's take one more column here in which I will write the OR gate output according to this input, and after that we will compare the output of OR gate and NOR gate, then we will see the difference. So what will be the output of NOR gate based on this input? We will write here. We know if any input of OR gate is 1, then automatically the output of OR gate will be 1. So for this one first pair, if you will see both input is 0, 0, here is no input is 1. So the output for this pair will be 0, because in OR gate, if all output will be 0, then only the output of OR gate will 0. So for that we are writing here 0. Now if we will see the second pair in which one input is set to logic 1, so we will simply write here 1 output. And the third pair, if you will see here, also one input is set to the logic 1, so we will also write here 1 as a output. And fourth one in which both input are 1, so we will write output of OR gate 1. So this is the OR gate output behavior. This is the NOR gate output behavior. Now if you are clearly see this both logic and the output values, then X is equal to complement of Y. Why we are saying? Because if you compare each value, then it is reversed value of X. If you see, if we will reverse the value of Y is 1 here. If we will reverse, then it will come 0. So 0 is the X value. Similarly, for the rest 3 case also, the X value is reversed of the Y value. So from here we are saying the NOR gate is a complement of OR gate. Okay, we have understood about the NOR gate. One important point that I want to suggest. See, lot of the student wasting their time to remember the whole truth table of each and every basic gate. So I'm suggesting one thing. No need to remember whole truth table of every basic gate. What the thing we need to remember is the functionality of every basic gate. So we have already covered the functionality of every basic gate. So we will remember one single line about the functionality of every basic gate. Like AND gate, if I will talk about the AND gate, we know if any input of AND gate is 0, then automatically the output of the AND gate will be 0 irrespective of the other inputs. Similarly, for the OR gate, we know if any input is 1, then automatically the output of the OR gate will be 1 irrespective of the other input. Similarly, for the NOT gate, we know the output of NOT gate is the complement of its input, and the NAND gate, as we know the AND gate, so NAND gate is nothing but it is the complement of AND gate. So if we will remember the AND gate functionality, then definitely we will write the NAND gate functionality in the truth table. Similarly, the NOR gate, it is the complement of OR gate. So if we will remember the OR gate functionality and the basic structure of the truth table, then we can simply write the NOR gate truth table as well. So before ending this video, I want to give some basic question for you. These are for basic question. You need to calculate the output value of each question. I have mentioned the input value. So just calculate the output and comment me in the video comment section. I hope this video is helpful for you. We will see in upcoming video the implementation of digital circuit using NAND and NOR universal logic gates. So stay connected for that. Thank you everyone for watching this video till end.